Okay, we are looking at 2016, number 6, part A. So if we look at that, and here's my pencil, number 6, part A. And I'm going to get just a little bit thicker here. I tend to write better. Okay, so it gives us the problem, and it wants us to find a Taylor series. And it says f at 1 is 1. F prime at 1 is negative 1/2. And then it gives us a rule for f at n. So that's the nth derivative of the function. And they say that, and again, they give us to that at 1, which we centered on. And that is negative 1 to the nth times n minus 1 factorial all over 2 to the nth. So look at that. We are going to find the Taylor series. So just to recall, the Taylor series, the coefficient is the nth derivative of the function f at n at your a, what you're set on, over n factorial. And then you have x minus a to the nth. That general pattern, or the formula for the coefficient on a Taylor series, and then a variable expression. So if I want to find the Taylor polynomial, I'm going to start with 1, and then I would have the next one would be the first derivative. So I would have negative 1 over 2, and then I would have 1 factorial, because that's n equals 1, and then I would have x minus 1 to the first. Then I would have plus. Now I'm looking at the second derivative. So I'm going to go up here. N is going to be 2. So I have negative 1 squared, which again would be positive 1. And then I have 2 minus 1 factorial over 2 to the second times 2 factorial. Continuing on, I would then have the next term would be putting in 3. So I have negative 1 to the third. Again, I could just write that as negative 1. And I have 3 minus 1 factorial, which would be 2 factorial, over 2 to the third times x minus 1 to the third. And then I have plus negative 1 to the fourth, 4 minus 1 factorial, over 2 to the fourth, 4 factorial. I need to go back here and add the factorial that I left off. So now there are my first 4 terms. Now, to find my nth term, I'm going to go back to this formula right here. So there will be a dot, dot, dot. And to find my nth term, here's where that dot, dot, dot is leading in. I'm going to take the f to the nth formula provided in the problem, which was negative 1 to the nth times n minus 1 factorial over 2 to the nth. And I'm going to copy that right after the dot, dot, dot exactly. Now I have to take that now times 1 over n factorial for the Taylor series rules. And then I'm going to take that times x minus 1 to the nth. So this is my nth term formula, or the general term. So now I'm just going to do some simplifying. So if I look at the n minus 1 factorial over the n factorial. So let's just go up here. N minus 1 factorial would be n minus 1 times n minus 2 times n minus 3, dot, dot, dot. Okay? And then if I take the n factorial, that's going to be n times n minus 1 times n minus 2, dot, dot, dot. So having done that, all of these will reduce with all of and all I'll be left with is an n in the denominator. So this portion of the general rule can be reduced to 1 over n. So going back to my dot, dot, dot from the previous screen, I'm going to have negative 1 to the nth over 2 to the n. And now instead of this in the green box, I'm just going to put the n from here after I reduced. And then I have the x minus 1 to the nth. So this is my general term. If they provide you with a formula for the nth derivative, that's how you start your general term. Just taking that formula exactly, and then remember, you have to multiply it by 1 over n factorial, because that's the part of the Taylor polynomial that we have its coefficient. And then you have the variable expression to the nth degree, and then you can reduce your coefficient. So the best case scenario is when they provide you a formula. If they do not provide you a formula, then you're looking for patterns. So let's say you have 2 squared, 2 cubed, 2 to the 4th. It's better not to write these as 4, 8, and 16. You would rather not write them out like this, because then it's harder to see the pattern. Because now I see the pattern is either 2 to the nth, or maybe it's 2 to the n minus 1, or maybe it's 2 to the nth plus 1. So a lot of the patterns involve exponential problems. So you don't want to simplify them to numbers if you're trying to establish a pattern. It's better off to leave them in exponential form, so then you can decide in the general term what the pattern is. The same is true for factorials. They tend to have factorials in them. So this would be 1, 2, 6, and then 24. You're better off not writing them like this and leaving them in this format, because then it's easy to see if it's n factorial or n minus 1 factorial or n plus 2 factorial, whatever the case may be. So when a formula is provided in the example here, this is best case scenario to find the general term. If a general formula is not provided, then you have to look for the patterns. And the patterns are sometimes hard to see, but that is the goal, to establish the pattern. I hope this helps.